Welcome back to Multigrid Methods. So we're again in Chapter 5 and specifically in Section 5.9, and we're talking about what happens when the standard Galerkin condition fails. So I want to start from the beginning. I'm not going to go through all the details that we went over last time. Uh, we're just going to look at them at a very high level so that we're back on the same page, and then I'm hoping to finish up this chapter today, or this, well, the section and the chapter. So again, we're talking about what happens when the Galerkin condition fails. So the type of condition that we're going to consider is what I'm calling a scaled Galerkin condition. So it's not the standard Galerkin condition. The standard Galerkin condition has two things going for it. The restriction and prolongation operations are a balanced pair. That is, they're both the restriction and prolongation are both full rank matrices of complementary size. And in the standard Galerkin condition, the restriction is the transpose of the prolongation. Here, in the Galerkin condition, we're going to break that. We're going to say we're going to have them to be related to each other, but not exactly a balanced pair. They're sort of balanced because the restriction is equal to the prolongation, but with a weighting constant r, which is between 0 and 1. Secondly, in the standard Galerkin condition, we also have the wrap condition holds. And here we're going to break that as well. We're going to assume in this section and in chapter 7 later on, we're going to show that we have a certain case which satisfies this, that restriction times A times the prolongation is equal to twice the stiffness matrix on the coarse grid. So the idea is we have this family of symmetric positive definite matrices, but they are related to each other not through the standard Galerkin condition, but through the scaled Galerkin condition. Well, if those two conditions on the previous page hold, we said, well, AL minus 1 is equal to R over 2 PL minus 1 transpose AL PL minus 1. Remember, again, the standard Galerkin condition, when that held, this constant out front had to be a 1. It's no longer 1. We talked about the fact that if assumption G0 fails, but G3 holds, the scaled Galerkin condition, then our coarse grid Ritz projection matrix is no longer a projection matrix. It's an almost projection matrix in that sense. However, if we take, well, let me not get too far ahead of myself. It is still true that it's self-adjoint with respect to the AL inner product, or symmetric with respect to the AL inner product. But if we redefine things in a slightly different way, we define this thing called the pi L hat matrix as 1/2 of the pi L tilde matrix. That thing is, firstly, it's self-adjoint with respect to the AL inner product. So A star is equal to the matrix back itself. And it's a bona fide projection matrix. The hat matrix is a projection matrix because pi L hat squared is equal to pi L hat. So we didn't prove that last time, but we mentioned it. Of course, anytime I have a projection matrix and I subtract it from the identity matrix, then it's going to be a projection matrix. And of course, if P is self-adjoint, then I minus P is also self-adjoint. Then we went on to show that for the two-grid matrix, or for the two-grid method, if we have certain conditions holding, even if the Galerkin condition fails, we can still have a convergence. The setting in which we're going to prove convergence is in what's called the alpha weak setting, or the alpha setting. We're going to assume that our method satisfies an alpha weak approximation property. Remember, we said that the weak approximation property or the standard approximation property is kind of associated with alpha equals 1. So alpha equals 1 is the standard case. That's not going to hold for our case in chapter 7. The best we can do in chapter 7, we're going to show that we can get this alpha weak approximation property, which we talked about previously. We're going to show in chapter 7 that we can prove this with alpha equals 1/2. Okay? So I'm not going to go through the details of this. I'm going to remind you that this thing exists and it's here. So an approximation property says something about the error in the course grid correction. And so that's obtained by looking at this matrix I minus pi L tilde. So this is a square matrix, and recall this is a square matrix. And so I want to show that in the AL norm or energy inner product, that this quantity is small in a certain sense. Now, one thing I want to point out is when we no longer have the Galerkin condition holding, then this guy is no longer a projection matrix. And so this object here is no longer non-negative. So we have to put absolute values around that. So that's an important point. So we talked about this last time. We talked about the first smoothing property. In fact, this guy is something that we've played with for a very long time. And if we use Richardson's smoother, as we're going to do and assume, then this first smoothing property is going to hold for Richardson's smoother. So that's a guarantee, and we can put that in our pocket and not worry about it. So we're going to assume that. And then the other thing I said we needed last time to get our convergence proof for the two-grid method is we needed a stability for Richardson smoother. So this KL, I'll just remind you, this is the error transfer matrix for smoothing, IL minus SLAL. So that matrix is stable in the AL norm, okay? That means that when I take the AL norm of this product, this guy goes away. And this is a little bit like saying the AL norm of the KL matrix is less than or equal to 1. So, and we have two stability statements that we proved with this lemma, but in fact, we only need this guy. And then last time we spent a fair amount of time proving the alpha convergence of the two-grid method. That means we're proving it with alpha not equal to 1, which is going to be the stronger case. So we can prove that we have convergence in this sense with assumption G3, that scaled Galerkin condition, so we can give up on the Galerkin condition. We don't lose everything. We still get some form of convergence. We are going to assume that we have the, let's see, this should be G3 and A2. That should be, yeah, I guess alpha weak is A2. I was thinking it's A3, but I was mixing myself up. So that's the alpha weak approximation property. So G3, alpha weak, and then we're going to use Richardson smoother, and we know that that satisfies the first smoothing property. Okay, so we'll be able to assume everything. And then we can prove convergence in this sense. This is a weaker convergence than we can get for the two-grid method in the standard setting whenever we're able to assume that the strong Galerkin condition holds G0 and that the strong approximation property A0 holds. This is weaker because whenever we have this alpha being less than 1, then this convergence constant is not as strong as it was before. So if alpha is equal to 1, we get a pretty small convergence constant. If alpha is less than 1, then this convergence constant becomes a little bit larger, but it's still strictly less than 1, as long as m, the number of smoothing iterations, is large enough. Now, I want to point out an important point about this analysis, and that was that we assumed that the method in our or in our two-grid method was symmetrized, so that the number of pre-smoothing operations is equal exactly to the number of post-smoothing operations, which is the common value m. And so if we make this large, then we can hope to make this whole constant strictly less than 1. If we take the 2 times alpha power, then that's still going to be less than 1. And so we're safe there. Right. So let's see here. So let me comment on what I meant by we get a reduction in convergence if alpha goes from, let's say, 1 down to a half. So normally, if alpha was equal to 1, then let's say this guy is small, so less than 1. So what would we know in the case where alpha is equal to a half? Let's call this guy gamma. So gamma, and we'll assume that gamma is less than 1. Well, in this case, we're going to get a gamma squared convergence, right? So gamma squared, if gamma is less than 1, how big is gamma squared? It's much smaller than 1, right? So let's say gamma is 0.7, gamma squared is 0.7 squared, which is much smaller than gamma. Now, what do we lose when we go to a weakened convergence? Let's say alpha equals a half. Well, if alpha is equal to a half, let's suppose that this is like 0.7, then our convergence is going to remain just gamma, right? Because here we have 2 alpha power, 2 times alpha is just equal to 1. And so we don't improve our convergence constant with that power. So we lose some speed of convergence. All right, so we do lose a bit by making these assumptions, but we still get a convergence. And that's the important thing. We don't lose everything. So we proved this last time. I argued that you can turn that as long as you know that E1 is symmetrized, or the algorithm is symmetrized by setting M1 equals M2 equals some common value M, then we can show that actually we can prove convergence in this sense. So that's left as an exercise. I had an error here that I want to mention. That's strange. So I thought I fixed that. Okay, I know what's wrong. Okay. I have the my iPad is not connected to the internet, so I simply transferred my old set of notes. And so I'll just fill in the corrections that I can remember. You'll actually have a better set of notes, a better set of slides than I'm actually working with here. I wanted to bring to your attention a typo, and the typo is here. This is missing a P. So if you've just downloaded the slides from Canvas, you'll have a P there, I hope. Maybe somebody can confirm that in the chat. You should have P here, not a blank space like I have. Now, in any case, so what I wanted to show, or what I wanted to argue, is if I have a symmetric method, and if I have this assumption, then I have, so the idea here is that this is some number, usually smaller than 1, that when I replace this 1 by a p, I can get an even smaller contraction for ELP. So this is something I mentioned last time, and the way that you can prove this is to use a Fourier analysis or a spectral analysis, because what we do know is that this is a self-adjoint operator as long as we have a symmetric scheme. If P is even, then you can go a little bit further. We can show, in addition to this result, that ELP is a symmetric or self-adjoint positive definite operator in the AL inner product. So what we always know is if it's symmetric, then EL is self-adjoint, and so that's good. What else do we know? So now if P is even, I showed you how to argue that this guy is positive semi-definite by breaking this into two pieces, throwing half of it over here. So we discussed that last time. It's just that I had the wrong thing here. So this is an estimate that we're going to need in the proof of the convergence of the W cycle coming up. So we talked about this last time. This result we also proved last time. So we're going to need this weird operation, and I'll show you where this is needed in a upcoming calculation. Now we realize that this object here is no longer a projection because pi L tilde is no longer a projection. However, this guy, pi L hat, is a projection, as we proved earlier, and we can use that to prove this very weird estimate that we're going to need. We went through the details of this. Last time I argued that that should be back here, right? That spacing issue has been corrected, or at least it should be corrected by the slides that you guys are looking at. All right, so let's go. We stopped there, and so this is now finally new stuff, and so we need to prove a couple of projection identities, which we're going to do now. So let's suppose that assumption G3 holds. That's our scaled Galerkin condition. I want to show that pi L minus 1 VL, pi L minus 1 VL in the AL norm, AL minus 1 norm. So this is like a, this is a norm squared, right? I could have replaced this by what? Pi L minus 1 VL AL minus 1 squared, right? So that's the same thing. It looks like a weird minus sign. There we go, equal. We're going to show that this object here is, for any VL in RNL, is equal to R times this inner product, which, because of the fact that this is a self-adjoint matrix, we could throw over on that side, and so it's the same as that. Now let's look at, before we go on, I like to always make sure everything makes dimensional sense. So does this make dimensional sense? This is a non-square matrix. This is a vector from R and L. It's arbitrary. So where does this matrix vector product live? It lives in R and L minus 1. R and L minus 1. So this guy and this guy are vectors of the same size. They're in R and L minus 1. Can I take the AL minus 1 inner product of them? The answer is yes, no problem. So this all works out dimensionally. But what about this? This is a square matrix, and this is a vector in R and L. Is this compatible for matrix vector multiplication? The answer is yes, this is square, and the number of columns is equal to the number of entries in that vector. So no problem there. That's going to give us a vector in R and L. I can take the AL inner product with VL. So everything makes sense there. What do I know about this constant here? R, I said before, has to be a number between 0 and 1. And now we see that makes sense because this guy, this object over on the left-hand side is a non-zero object, right? Because it's a norm squared. So this object here, does that have a sign? The answer is, well, not necessarily. It's not clear what the sign is, right? R has a sign, but now what we can say by the virtue of the fact that this is non-zero, non-negative, then this actually does have a sign. This has to be apparently greater than or equal to 0, as does this guy. Okay, so that's good. Everything is making sense so far. So we're going to show this. Similarly, for all L between 1 and capital L and any vector VL and RNL, and every matrix that we want to cook up, BL minus 1, from this set of matrices, then we can show that this identity is true. What are we doing? What are we doing here? So it looks like so on this side we have BL minus 1 pi L minus 1 VL, and here we have pi L minus 1. You know, what it would be nice to do is to take this guy, lift it, and put it over here, and just leave VL by itself. If we do that, you know, we could do that. We're going to have to do some ratcheting of spaces, but what we're going to show is that when we do that, what we get is we get an R and a PL minus 1 over on the other side in effect. And we change from the inner product space, or the inner product in AL minus 1, which is a lower level inner product, to a higher level inner product AL. So that's what we aim to show, this result and this result. Okay. Now let's first start by recalling a definition. So you might recall this thing defined in the following way. Pi L minus 1 is equal to AL minus 1 inverse RL minus 1 AL. That definition is rock solid and always true. We're going to leave that defined in that way always. So the pi L minus 1 matrix, always defined like that. However, this matrix is symmetric positive definite, so we can multiply both sides by its inverse, which is just AL minus 1, and so we immediately get that identity. So that's where we're starting. Okay, we recall that identity. Now, we want to show that this guy works out to be this, so let's figure out how that happens. Let's start out with this, this object on the left-hand side, and let's play around with it. Now, if we're operating in the AL inner product, we can always change that to a canonical inner product on level L minus 1 by multiplying on either the right or the left this matrix AL minus 1. That's how this guy is ultimately defined. So that means we're just moving that guy in and attaching him there. Now, once we have that, by the definition of this and this little identity here, we can see that we can replace any instance of that with that. So that's what I did. This I replaced with RL minus 1 times AL. Okay, so far so good. This all stays the same otherwise, and we don't need to do any other changes. L minus 1, L minus 1. Now let's see what we get. Here, let's take this object and throw it to the other side. And if we do that, we pick up an adjoint, just the transpose. So we get RL minus 1 transpose. Okay, so we also have to ratchet the inner product from L minus 1 to L. No problem there. Now we can replace this object by our Galerkin assumption, or assumption in the Galerkin condition. One of those is we have this off balance. We no longer have a symmetric balance between R and P. RL minus 1 transpose is equal to, it's easy to show, R times PL minus 1. It's very easy. We said RL minus 1 is equal to R times PL minus 1 transpose. Take the transpose of both sides. If you do that, the transpose doesn't affect the R. And so this just becomes a P, and this becomes RL minus 1 transpose. If I plunk that in there, then I get R times PL minus 1. The R I can bring all the way out front. All right, fine there. Now, by definition, this is the pi L tilde matrix, that's just what pi L tilde is. Okay, it's defined as PL minus 1 times pi L minus 1. That's pi L tilde. We have the AL norm or the AL matrix here. We can always pull that guy out, no problem. So let's take this guy and pull it out. And so we get pi L tilde VL against VL, but we also have this R parameter here. Now, that's interesting. That's interesting because we know that pi L tilde is self-adjoint. Still self-adjoint, so we can throw that guy over to the other side. And so both of these then hold. Okay, both of those facts hold. And curiously, what we're showing is this object here is greater than or equal to 0. R is strictly positive, so this object must also be greater than or equal to 0. It's something I should have added in there. Now, how do we get the second identity? The second identity I'm going to leave for an exercise. It doesn't look like I've made it a specific exercise, but I think it's a straightforward exercise. In the book, I may have it as a homework problem, but I'm not sure. All right, cool. So let's move on. Now, let's see. Okay. So now I want to show the alpha weak convergence of the W cycle method. So what do I have to show in this case? Well, I have to show that I can find some gamma such that this holds. And so that's what I'm going to try to show. Now, I'm not going to fix M. I'm simply going to take M large enough so that I can achieve my convergence goals. Okay, so I'm going to symmetrize my algorithm. I'm going to use P even because somewhere along the line, if I use P even, I can take advantage of something that I said or mentioned earlier. If I use the fact that P is even, then this guy is going to be self-adjoint positive definite, meaning that's going to be true. So I can use the fact that I'm going to use the fact somewhere that that I have this sign on this object. All right, so that's why I'm going to take P even. I'm going to assume that G3 holds, so that's my scaled Galerkin condition. I'm going to assume that alpha weak approximation holds. We're going to do smoothing using Richardson's smoother. What do we know if we use Richardson's smoother? If we use Richardson's smoother, then that means that that the first smoothing principle holds. So all good there. So that means we can apply the estimates of the first smoothing principle, which we will do. Then for any gamma that we want between 0 and 1, that's good. We want this thing to be small. There is an M such that, and remember, this means that we have to do, this means there is an M. That means there is a barrier for the number of smoothing iterations that we do, so that if we go over that barrier, then we're going to get convergence. Okay. So there is a minimum amount of smoothing that we need to do, such that for all L, the W cycle error matrix satisfies that. In particular, it suffices to choose an M that satisfies this condition, and then we'll get our convergence. So M has to be bigger than this amount. Okay, how big is that amount? I don't know. Let's throw some numbers at it. Suppose that I want to choose gamma to be 0.5. So that's going to be a half. All right, so let's say I want to achieve the convergence gamma equals a half. That's a reasonable target. Let's say we take P equals to 2. P equals 2. Let's suppose that the best thing I can achieve here is alpha equals to a half. Okay. How many smoothing iterations am I going to have to take to achieve convergence? Well, I don't know how big these constants are. Let's assume that those guys are equal to 1 in both cases. So let's say, okay, CA2 equals 1 CS1. Let's suppose I really could achieve that. That's probably not possible, but okay. So now this tells us exactly how many smoothing iterations in the worst case scenario we need to obtain in order to get convergence. So this actually is a fairly practical little result for us. Okay, so M has to be greater than 1 minus, so we said that gamma has to be 1/2. So now we know that this is going to be 1/4, right? And then on the bottom, we have 1/2 minus 1/4. What do we have for our exponent? We have 1 over alpha, which is 1/2, so that's going to be squared. So this works out to be 3 over 4 over 1 over 4 squared. So that's equal to 3 over 1 squared, which is equal to 9. So this tells us that we've got to be bigger than or equal to 9 smoothing operations pre and post in order to guarantee that we're going to get convergence. So will 9 work? Well, according to our theory, it should work. As long as we have m greater than or equal to this number, in this case is 9, then we're going to get convergence. So hopefully we show all of this as we're doing this proof. Now, I will say, in practice, you won't know the size of these two objects here. You just can't know that, and you're just going to have to guess at those. And so what would be safe? I don't know. It'd probably be safe to say these guys are at least 2, maybe 4. So if they're at least both 2, then things are starting to get bad, right? Because, well, if they're both 2, then this is 4 times 4. So this has to be 16 times larger. That could be bad, right? But, you know, that's what it is. All right, so let's do the proof. Now, in the notes that you would obtain for Canvas and that you can obtain from GitHub eventually, I spelled out on a previous slide exactly what the error transfer matrix is for the W cycle, but here it is again. This is our error transfer matrix for the W cycle for generic P. We could also call this a P cycle if we want, because typically when we say W cycle, that's for P equals 2, but let's not worry about that. Okay, so we've got to operate with this object here. The nice thing is, well, we've symmetrized the method, so M1 and M2 are the same. So this object is self-adjoint in the AL inner product, which we showed with an earlier result. However, we can't necessarily conclude that it's positive semi-definite. All right, so this guy is not necessarily, it's not even necessarily non-negative semi-definite. We don't know the sign of this. I should have said that here. It's not necessarily non-negative semi-definite. Oh no, that takes care of it, right? When you say semi-definite, that takes care of it. I don't have to say non-negative. Okay. Not necessarily positive semi-definite. We don't know the sign on this guy. It is, however, definitely self-adjoint. We're good there. So that's what was guaranteed in the previous lemma. Now we're going to have to evaluate this guy. We're going to have to evaluate, or makes it useful to evaluate with this vector. WL is equal to KLM VL. So what we're going to assume here is that VL is any arbitrary vector VL from RNL whatsoever. When I put VL in that position and I use my definition of EL here, then what happens is I can take I first take this operator here. This is the post-smoother operator, or at least the error transfer associated to that. And I'm going to immediately move it over to the other side. So it's going to be here and I'm going to move it over to the other side. And I can do that because, or I should say I can do it, but it's going to gain a star, right? It's going to become the adjoint. But the nice thing is it's already adjointed. And I've got m powers of those adjoints. Each one of them can taken over as an adjoint, but I'm going to take it over as an adjoint of an adjoint. And so that just becomes the same thing back. So what happens when I move that guy over from here to there, I get two copies of this W vector owing to that definition. Now, that I get it in two places. And so I get it there and there, but I also have to, because this definition is not so simple anymore, it's not just this and this. I've also got these other operators in the middle here. So that means I have to split this up into two terms, and the second term is right here. Okay, so that might be or seem complicated, but there is an extra term that I get because this guy here is present. Now, if you're working with 2-grid, 2-grid does not have that guy there, and so 2-grid would just have this against that. That's this matrix right there. Okay, so you see you get one extra matrix because of the presence of that guy, and that appears here. All right, now what about this 1 over R? Where did that guy come from? Well, that guy came from this estimate that we did. I think it came from, let's see. That guy came from here, 6. Okay. Notice that we have some matrix. I don't know what it is. Maybe it's the E matrix. Okay. But when we do some arrangement, bring this guy to the other side, we get an R here, and then we change levels of our inner product. So that's 6. And so I claim that from the definition up here, this definition, then using 6, then the second term becomes this. Okay, so hopefully you'll check that, make sure that's all right. But we start working in the AL inner product, we switch to AL minus 1, so I think it's perfectly correct. Okay, so this is the thing we're going to have to work with. So let's see. So now we begin our proof of convergence, and up until this point, I guess, all we're doing here is just settling in using our definition for the error and figuring out what is that object we're going to have to work on. So we're going to have to show that this is less than that. And so the object that we want to work on is this, but that transforms into that. Okay, now we're going to have to take absolute values of both sides and see what we get. Well, of course, we probably want to do an induction hypothesis here. The reason we want to do induction is we want to leverage a previous lemma that we have, and we also want to take advantage of the fact that this error transfer matrix is simpler at lower levels. Okay, for the level L equals 0, we have no error at all, because the error transfer matrix at level 0 is defined as 0, or is that we can show it's just 0, because what we're doing there is an exact solve. What about level 1? Well, level 1 is just 2-grid, and so that's true, or the hypothesis is true by virtue of what we proved previously. We already showed that the 2-grid converges. So that takes care of the two base cases. So the induction is going to be done on levels as L gets larger and larger, which kind of makes sense. So the induction hypothesis is going to be, let's suppose that the result holds true at the lower levels. Okay, at level L minus 1, we'll assume that we have, for any gamma, that we have this bound holding, as long as M is sufficiently large. So that's the idea of the induction hypothesis. Now, let's further assume that P is even. So that was part of our assumptions. P is even. So P being even, we said that means that this matrix is going to be is going to have a sign, right? And it had to be this full matrix here. So before I forgot to put on the P, but now we know the P has to be there. So this matrix is non-negative definite. And so we have a sign on this object here. And we're assuming it's true because we're operating on level L minus 1. And so we get this. We can replace that with having the absolute values in place, right? But now by our induction hypothesis and a previous lemma, which we hope is true, we can guarantee that this object is less than gamma to the p power times VL minus 1 VL minus 1 in the AL minus 1 inner product. So that was that previous lemma that we did improve. Okay, or the result of that lemma that we did improve. Cool. Okay, so that's where we are. So if we assume the induction hypothesis is true, then we can immediately prove that that is greater than 0 and less than, in the upper bound, gamma to the p power VL minus 1, VL minus 1, AL minus 1. Now, this object here is as long as VL is not, L minus 1 is not equal to 0, this is a positive object. This is a positive number. So, we can see that this pins, these two numbers here pin this object. Okay, it kind of gets trapped between 0 and something which is approaching 0, right? So the squeeze theorem tells us that if we tried to make gamma larger and larger, that would become as small as we please. It would go to 0. Okay, so now let's use our identity, the identity that we established in the first part of the proof. So we said, let's settle in. We know we have to approximate that object. It breaks into two pieces. The second object has this weird 1 over r term, which is appearing. We're going to show that that 1 over r actually goes away shortly. But before we do that, let's see what we get. Now, this object here and this object here, they're the same, no change. We said that we can replace this with that. And why can we do that without a change of sign? Well, that's just this statement here. Now, we're not using some arbitrary VL minus 1 there. We're using that guy and that guy. That's playing the role of our VL minus 1 at this point. So we can replace or put the P on a gamma P over R, and get rid of that error term. Okay, now we're going to apply our identity 5. So this term doesn't change. This stays the same. So what was identity 5? Let's go back and have a look at it. So what we're saying is we want to get rid of this R. And so we want to replace this term with R times that term. And that's exactly what identity 5 says you can do. See, there's identity 5. So that's the term we're replacing. And we can replace it with either one of these two, but they both carry an R. Oops, where was I here? There we go. Nope. Here. Okay, so I replaced that object using identity 5. All right, now I can combine a couple of terms. Let's see what I can combine. So let's break this guy up into two terms. There's no absolute values in sight yet. So I'm going to break that up into a term that involves pi L tilde WL WL, because this term also is of that structure. We're in the same inner product. We know that inner products are linear in their first and their second arguments. So we can combine these two results together to get 1 minus gamma to the p power, coming from this term, of 1 minus, oh, I see what I'm doing. Actually, what I'm going to do here is I'm going to add and subtract the identity in this case. All right. So actually, let me just think about this. Make sure I've got all my signs correct. Right. So this guy I want to change to a minus sign. So this is going to be minus a minus. Then I'm going to add and subtract the identity. So what do I need? This is the subtraction of the identity. So the added identity is there. Okay. So yeah, everything does work out. Okay. I probably should have written an extra step, but I was trying to save some paper, and I think it's not too hard to see that this line gives that line. Now, what is next? What is next? I already know that this object is positive. I don't know the sign on this object. I'm going to therefore put an absolute value around it. Why don't I know the sign of this object? Previously, when the Galerkin condition holds, I do know the sign because this object here is a projection matrix. So if I knew that the Galerkin condition held, I could replace this 1 with a 2, and then I could throw the object, one of them, on the other side, and I would see that this has a sign, it's non-negative. And so I wouldn't have to put this absolute value in that case. However, for this object, I no longer have this as a projection, so I don't know the sign anymore, and I have to put an absolute value if I want to get control of the size. So that's what I'm doing. I'm replacing this with an absolute value. So if this is minus 5, I'm just replacing it with plus 5. This object here, what do we know about the sign of that? 1 minus gamma to the p is of course a number which is less than 1, but greater than 0. Okay, so this guy is a positive number by virtue of the fact that I'm asking gamma to be less than 1. So gamma to some positive power p, some positive even power p, is still positive. Okay, I think I've got everything there. So now I know that's less than or equal to that, and so to do further analysis, I can copy that over. Now, before I do that, let's put a minus sign in front of this guy and see what we get. Well, let's go back for a second. Let's see. We started out with this object, so I'm just going to put a minus sign in front of it. Minus, minus, minus. Okay, why am I doing that? Well, I have a previous lemma that had an estimate which tells me why I might want to do that. So let's do it. Put the minus sign there. So that gives me a minus and a minus, the usual thing. But now I know that this guy here, what do I know about this object here? This is a positive, or at least a non-negative number, right? I know that that's a non-negative number, so I can get rid of that guy. So this is like, this I don't know the sign of, right? This is going to be like minus 5. What happens if I replace that minus 5 with a 0? I go up, right? So I have some number which is greater than or equal to that number. Replaces, this is a signed number, right? And why is it signed? Because even though we can't say anything about EL minus 1, EL minus 1 to the p power is non-negative. So I'm good there, right? It's non-negative definite. So this whole thing has a sign, and the whole term is negative because I put a minus sign in front of it. So it's like replacing minus 5 with 0. Okay, so I'm going to get something which is larger. Very good. Now here I'm going to add and subtract a term which doesn't change any of my results. So I'm going to add and subtract terms so that I get this. So I'm going from here to here. I'm not changing a single thing. So I want you to check that, make sure I'm right, but I'm pretty sure I am. I'm adding somewhere along the way this term and then subtracting it out. So that gives 0, and I combine it with this. Okay, so there's the plus and there's the minus. We're all good, right? Now, from estimate 4, which we're going to go back and look at, that was something involving this term here. Okay, so let's go back and look at estimate 4. So estimate 4 said I can replace a negative something involving that guy with that term, which doesn't have that error. Okay, so let's see. That's what we have here. And I'm going to replace this with a positive term. The gamut of the P, because that's a positive number, doesn't change the direction of that inequality, so I'm okay there. This doesn't change from here to here, so I'm okay there. All right, now I'm going to take absolute values of this guy, to just take absolute values of this whole thing and use a triangle inequality. That's still valid, no problem. And so that gives me an absolute value of here. What about the absolute value that would have been here? Well, it's not needed because this is already a positive number. It's known to be positive. Okay, that's cool because without doing any real analysis here, except we use this weird estimate 4, which I said was going to be useful to us, I showed that minus this number is less than this number. Okay, well, I already previously had that EL. Let me put it in completely general terms. I previously proved that X is less than or equal to a positive number A. I also just showed that minus X is less than or equal to A. So what does this mean? Well, it means that the absolute value has to be between, you know, this proves that the absolute value has to be less than or equal to A. That's what I just showed. Because I previously had this same estimate, but without the minus sign here, the plus sign there. And that one did use the induction hypothesis, etc. Okay, so the induction hypothesis came from this step. I probably should have said induction and then an identity. But in any case, this side, we really did use some analysis and got X is less than A. And so here is minus X is also less than A. So the absolute value has to be less than A. Okay, cool. So if we combine those two estimates, we get exactly what I just said. Absolute value of X is less than or equal to A. That's just this. So now to conclude, we're going to use an error estimate from the 2-grid method, and we're going to use the stability of Richardson smoother to obtain the result that we want, provided that 7 holds. So what was 7? 7 was my assumption about the size of M. Okay, so 7 is the size of M that I'm choosing. Provided that holds, hopefully everything is going to hold. So, right. So, what does the 2-grid convergence method show? Well, that guarantees that we're going to have this guy here less than some number. And the number that we can show that that's less than is all of this guy, right? This I can't change. I can't do anything with that. Okay, so I'm just going to have to compile it together. Now, here is where I needed to use the convergence property of the 2-grid, or I should say, to get the convergence property in the 2-grid method, I needed to use two things, or a few things. I needed to use my alpha weak approximation. So that's that guy. And I also had to use the smoothing property. So, well, Richardson's method satisfied the smoothing property, so I got that. So this is exactly the same constant that we got when we proved the convergence estimate for the 2-grid method. So we just showed that is less than that. Now, we didn't exactly show that, that this was less than that. We just realized now that buried in the definition of this WL are the K matrices, the error transfer matrices for the smoothing. Now I'm going to take this guy, the K matrices over here, and I'm going to put that guy back. Okay, so that's going to give me, for this step here, that's just the 2-grid error transfer matrix. And so the reason why I'm converting from WL to VL here is because I've made this transformation from this object to the 2-grid error transfer matrix, and then I use the convergence estimate for that. Very good. Okay. Now I get the same thing here. And what about this? So here I have to use stability of Richardson's to get rid of the K matrix that's here. That stability estimate was a few slides ago, but in any case, that's why I'm able to change this one from W to V. That's stability. Now these things are truly the same. Okay. And notice I had to use stability when I proved the convergence of the two-grid method, and I have to use stability once again to get this overall convergence. Okay, so now, as I said, I have the same thing here and here. I'm just going to combine these two objects together. Okay, now you have to unfold things a little bit, and you have to prove a little estimate. If I know that M satisfies 7, then you can show it's not a hard little estimate. You're just going to kind of unpack 7, convert it into this form. What I'm going to show is that that is less than gamma. So what I'm saying is this whole thing here, less than or equal to gamma, is true if and only if 7 holds. Okay? Let me say that one more time. So this number, the sum of that number being less than gamma, is true if and only if 7 holds. If they go both ways. So if 7 holds, then this has to be less than gamma. Boom, I'm done. And that is the convergence proof for the W cycle. Now, again, I have to take M large enough so that this can be less than gamma so that I get convergence. And the nice thing is that doesn't change at any level that I'm at. It's the same gamma or the same value of M that I would have to use at the previous level. And so that's already part of the induction hypothesis. So we're good to go there. Okay. Now, as I said, we have to be able to take M large enough. And we said, you know, you may have to take M pretty large. Here, if CA is equal to 1 and CS is equal to 1, then we have to take M larger than 9. That's already pretty large, a large number of smoothing iterations for my method. But if this is just equal to 2 and this is equal to 2, then the square is equal to 4 times 4, that's 16. So already that's 16 times larger. Then that's a lot of smoothing iterations to do. And remember, we said smoothing iterations actually cost real dollars. They have a computational cost associated to them, which turns out to be potentially rather expensive. However, let me point out that this is what's called an abstract convergence result. It's a worst case scenario result. What we can show is that in practice, you don't need to take anywhere near this number of smoothing iterations to get a convergence. You can still, instead of having 100 smoothing iterations, well, if it's 9 times 16, that's well over 100. Instead of having that many smoothing iterations, you can still get away with taking just 3. And we're actually going to prove that. We're gonna actually prove that with the next result. Now, the next result is an absolute, well, there is one small result in between this and the next big result. The next big result is an absolute killer. It requires a lot of neurons and brain cells, and I probably won't be able to fulfill my desire of getting through all of the slides for chapter 5 today. So we're not going to try to conquer that next result. It's just too much of a beast. And I do want you to see it in some detail. So let me just state this corollary, which is the small result I was talking about. And we'll talk about a couple technical lemmas needed to prove the next big result. But the next big result is actually a much, is quite an improvement over this convergence result here. And the next result, we're going to show that you don't have to take such a large number of smoothing iterations to get convergence. In fact, it's enough to take one smoothing result or 2 or 3. You don't have to take 160. You can get away with a fairly small number. So that result is a real killer, and it's going to require some hard thinking, but we'll get to it. To finish that last result off, I should say one thing. We can use what we just proved to prove a convergence in this sense. And so I'm going to leave this as an exercise. It's it's more or less related exactly to the last corollary that we stated, the convergence for the two-grid method. Basically, it uses that last result plus the fact that E is self-adjoint, and using a basis expansion for V, you can show that using the eigenvectors of this matrix, which are known to be self-adjoint and not self-adjoint, ortho we can find an orthonormal basis in the AL inner product of eigenvectors for this guy because it's self-adjoint in this inner product. So you use that basis of orthonormal eigenvectors from this guy, and you can prove the previous result gives you precisely that without any changes or anything like that. And then this truly is a convergence result. From this we can say basically that EL in the AL norm is less than or equal to gamma. Okay, so that's the convergence that we're talking about, provided M is big enough and blah, 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 and P is even, etc. So same result. All right, so now, as I said, there's a lot of room for improvement because we have to do a heck of a lot of smoothing potentially to get convergence in that last W cycle algorithm. A heck of a lot, right? So I said using some fairly mundane numbers, we might have to do 16 times 9 smoothing iterations pre and post in the pre and post smoothing operations. That's a lot. That's way too many. That's almost 160 smoothing iterations. But the next result I want to show you, you can actually prove that you get convergence even if M is equal to 1. Okay, even if M is equal to 1. So how do we do that? Well, it requires a heck of a lot of technical lemmas and a heck of a lot of work. So let's take this slow. And like I said, we won't be able to finish this section off today, but we'll finish it off, I hope, next time. All right, so the first thing I want to do is talk about a Young's inequality that we're going to need. Sometimes people call this the rob Peter to pay Paul Young inequality. And so it's a fairly straightforward application of the general Young inequality. So let me tell you, the general Young inequality is A times B is less than A to the P over P plus B to the Q over Q, where for any A and B, where 1 over P plus 1 over Q are equal to 1. The sum is equal to 1. So P and Q are called conjugate variables. P has to be in the region 1 to infinity. And if that's the case, then Q is given by that. In other words, Q satisfies this inequality. Now, this is the usual standard Young inequality. And of course, yes, it does hold if I put P equals 1 here, but there's a kind of then you kind of have to do something slightly different. Otherwise, that's kind of a barrier case, and we want to consider this this case where P and Q are between 1 and infinity. So if I know P is between 1 and infinity, then its reciprocal Q has to also be between 1 and infinity. All right, so that's the standard Young inequality. What is this new rob Peter to pay Paul Young inequality? Well, from this one, what I can do is I can put in here, I can break this one, right? I could rewrite this guy as there's lots of ways you can prove this, but basically I'm going to say A times B is equal to A over some epsilon times epsilon B, right? And then if I apply my Young inequality to this guy and then judiciously choose epsilon, I can show right away that I'm going to get this, inequality here. For any alpha between 0 and 1, so really I have to choose this epsilon judiciously, and the P is going to come out naturally. All right. And any tau, so the epsilon is related to tau, or I should say tau is related to epsilon, and the alpha is as well. But I can choose them any way that I want so long as tau is positive and alpha is between 0 and 1. Then this results from the Young inequality here. So you're going to confirm that in a homework exercise. Now, in particular, if I choose P equals 1 over alpha and Q equals to 1 over 1 minus alpha, let's first of all do a sanity check on this guy and make sure it makes sense. Well, if alpha is between 0 and 1, if I take its reciprocal and call that P, that number is going to be between 1 and infinity. Check. Okay. And as I said before, Q, if I take it to follow this prescription, which is exactly what I'm doing here, using that particular value of P, then it is also going to be between 1 and infinity. Check. Okay. So now I'm just going to sub in what those values are. So immediately here, tau alpha P, well, because P is equal to 1 over alpha, this just becomes tau. Where did my alpha come from? Oh, yeah, because I have a 1 over P here. So tau to the 1 over P is going to be 1 over alpha. So that's alpha in the numerator. And then, right, everything's falling out, looks like. So actually, that's the proof. You don't really have to do much. You just kind of have to say, well, if I start with, I know this inequality, and I rewrite A times B like that, choose epsilon to be judiciously related to tau and alpha, then you should get this. And if I choose P and Q to be that, then I should get that. Okay, so I'll leave the details to you, but we will need this very odd and painful looking version of Young inequality. Now this one, there's no way in, haven't got a snowball's chance in where to get this guy done in today. So I'm just going to give an overview of this, and this is where we will start next time. Okay, so this technical estimate is pretty painful. And let's see, do I even want to prove it? Maybe I do. I don't know. It's pretty painful. Oh, it's so painful. Oh, it's painful. But let's at least get through the statement of it, and I'll toss a coin over the weekend and think about whether I want to do it or not. Okay, so suppose that k is any number which is greater than 0 and alpha is between 0 and 1. Then we're going to define this object or this number called k alpha. And how big is k alpha? Well, I don't really know, but let's just make sure that it's all makes sense. It's 1 minus alpha to the 1 minus alpha power. Okay, if alpha is a half, that makes sense, then this is going to be a half to the half power. Okay, that looks like it makes sense. And a half to the half power. So that makes sense as well. And k to the alpha power, that looks like that makes sense. So all I know is that this is probably, I'm pretty sure it's some positive number that we're going to need later. Define for x between 0 and 1 inclusive of 0 and 1, and beta between 0 and 1, but exclusive of 0 and 1, and any m in n. I'm going to define this function. So it's a function of three variables, beta, x, and m. Okay, so if I put in different values of beta, different values of x, and I have different values of this integer, positive integer m, I should get different function values here. Okay, so that's the thing I'm going to call gamma, and it satisfies that. Cool. Now, notice that this guy, of course, depends on my value of k. I could have said this guy is dependent on k as well, but let's not make things harder than they need to be. K is fixed. All right, so good. Right, so I'm going to fix k in alpha, then I can define this thing called gamma. Okay, we're all set there. Assume that m is chosen so that it is bigger than the max of this number, 1/2 4k to the alpha, 1 over alpha, and m to the alpha. Okay, so I can always do that, no problem, because this is some positive number, and that's a positive number, and I can choose bigger than the max. Okay, fine. Then it um, then it follows that if I put in a delta squared for this term here, for beta, for any x and any m, gamma delta squared xm has to be strictly less than delta, or not strictly, but less than or equal to delta, where delta is equal to a particular value, m over m plus m to the alpha power. So we're going to show that next time. This is a typo here because that should have been a period. So this technical lemma, I'm either, like I said, I'm going to flip a coin. I might do it, I might not. If we don't do it, we'll just, assume it's true and go from there.